Alright, welcome back. Today I'll be talking about the virology of HIV, influenza, and SARS, specifically SARS-CoV-2. Okay, so I'm starting off with talking about HIV. HIV is a retrovirus. Starts off 5 to 3 positive or since. And importantly, as opposed to influenza and SARS, it does not use receptor-mediated endocytosis. Instead, the HIV, how HIV enters the cell is a fusion event. So you can give 2 water droplets kind of touching. What happens is these little receptors on T helper cells, CD4 positive T helper cells, have receptors that are, CD4, and they have co-receptors, CXCR4 and CCR5. So this is diffusion. You can kind of imagine as this, it pulls in the 2 together, and as you pinch off something, it'll combine. So that's how HIV enters. So let's draw HIV here, and it has these little glycoproteins, which I should have mentioned that is how it attaches to the receptors. And it has its capsid here. The capsid is a protective formation over the viral RNA, which has a nucleocapsid, which containing all the enzymes that can enter the cell. So this enters the cell and it's pH dependent. That's why it's not receptor-mediated endocytosis. The capsid breaks off into the T helper cell. That's on the nucleus. You have this positive stranded vRNA, and what happens is you have RNase or reverse transcriptase, which is going to form RNA. Or not going to form RNA. RNA is already there, but it's going to form a combination of DNA and RNA. This DNA is antisense, like all good DNA that must be transcribed does. So this is antisense. Put AS, and I'll put AS here. This is converted into a homogeneous mixture of DNA, antisense DNA, because RNase also acts as a digests RNA. So after love with that, we can have DNA dependent. Let's count my mouthful. I'm gonna write it here. DNA dependent DNA transcriptase. So what that means is now we can form double-stranded DNA, or dsDNA, from our antisense. So the thing about dsDNA is that's how the genome works, right? It's double-stranded. So dsDNA can enter through the cell via integrase and, integrate with the genome. So now we're left with a T helper cell that has now been replaced the part of the genome, which is why DNA viruses like HIV can cause cancer directly, because they can bind to, parts of the cell that control cancer, right? PC53, the P53, like P53, I think it is. P56, I'm not sure, but genes that code for that can be affected. Or other cancer blocking mechanisms. So now that we have our viral DNA integrated with the host genome, another key thing about HIV is it doesn't have its own viral RNA polymerase. Instead, it uses the host RNA polymerase. So what's here is now as this gets read off, via translation, transcription, it's not forming the wrong kind of stuff, right? It's forming viral nucleocapsid proteins. It's following the regular capsid. It's forming more viral RNA, sense RNA. It's forming the glycoproteins, which start falling off here onto this. These will form in here. All our enzymes and proteins that we can use to infect the next cell form up here, and this begins to bud off. Okay, and this blobs out, and with like little RNAs, they go in and hurt more people. It's not good. So yeah, that's HIV life cycle. Now we can talk about a pretty interesting one and quite unique for a lot of viruses, I suppose, is influenza or the flu. Okay, so the flu, influenza A, is a negative antisense strand. So there's a couple of unique things about it. Okay, so let's start about it first. So influenza A has 3 methods of entering a cell. Okay, the most important one, the primary one, is clathrin-mediated endocytosis. So clathrin-mediated endocytosis also has caveoli-mediated endocytosis, which I guess is kind of hard to distinguish. I put a little A there, a little L here. So, and then it could also go through macropinocytosis. Cytosis. So these are pretty similar, and for this exam, you really just need to know this one. You need to know that these also exist. Macropinocytosis is kind of like the cell engulfing the virus. It's one method of how they do it. But in general, we use clathrin-mediated endocytosis. Oh, not we. mean the viruses. They enter through this clathrin-mediated endocytosis, which is basically clathrin accumulates on the cell surface, which receptors that can bind to this. By the way, the receptors that it binds to are celiac acid receptors, and it binds them via hemagglutinin. Hemagglutinin. So that's these little receptors. It also has these what's the name for them? Neuraminidase. So you can kind of imagine this like, I guess, like a triangle or something. So it has these hemagglutinin. Hemagglutinin can bind to the celiac acid receptors. Via clathrin-mediated endocytosis, they're brought into the cell. So what is interesting about this influenza? Well, we have our uniquely antisense. Not uniquely, I guess, I suppose. We have our antisense. And this is 3' to 5'. So what's interesting is as this enters, and this is a lysosome, and we're forming a vesicle based on the clathrin-mediated endocytosis. The lysosome is going to come in here with our capsid here and our viral RNA. It's going to degrade that down, and the pH here is going to get very, very low, like 4 or 5, which is going to help break up that capsid. So once that breaks off, it can leave in here. And what's interesting about influenza, and this should not be reflective of most viruses, but influenza can enter the nucleus, like HIV. So that's kind of weird. And we're left with 3' to 5' antisense in the nucleus. Now, this can be, has its own, unlike HIV, it has its own vRNA transcriptase. Yes, vRNA transcriptase, yeah. Transcriptase. And this can get converted to sense. I'm going to draw them as positive and negative. This is negative, positive, negative. Okay, so that's how I can form vRNA back into the system, which can leave for later. So let's keep that in mind. Additionally, you will have your sense create the nucleocapsid. It's going to create the clathrin-mediated. It's going to create the capsid, nucleocapsid capsid. It's going to create the enzymes in the nucleocapsid. It's going to create the viral proteins. It's going to create the receptors, which again will kind of edge the thing. So we're left with our negative here. So we're all going to go in here and form up, which can then leave the cell. So an important thing to note is that sometimes when it's leaving here, you have celiac acid receptors, and they kind of latch on to the hemagglutinin. And so the way that influenza has evolved to deal with this is it has these neuraminidase, and these neuraminidase can cleave celiac acid, which is like getting your foot stuck and then pulling it out. You know what I mean? Or chopping it off to. No. It's just like if someone grabs your foot and you cut off their arm. So then it spreads out, and that's how influenza can spread. Okay. Now on to back when this happened, this was like, I was in high school. And freshman and sophomore year. So what was interesting with this is SARS-CoV, or a lot of SARS, acute respiratory viruses, they can be found in a bunch of different names. I mean, these things like to evolve. We got MERS, we got SARS. What else do we have? SARS-1. The common cold, obviously. This is some variants on SARS. But for COVID, let's draw COVID out here. So he's got his little glycoproteins. And on the cells that he likes to infect, these guys have ACE receptors. ACE2 receptors. So these, or I guess they're an enzyme, so he can bind to these ACE2. Sometimes he can even have TMPRS2. Is that right? TMPRSS2. TMPRSS2. So he can bind through here, and just like influenza, you can go in through clathrin-mediated endocytosis, which I'm not going to draw out, but it's vesicle forms, lysosome comes in, breaks apart the capsid. But you can also have TMPRS2 cleave these two membranes, which causes a fusion event. So that's pretty important. And then for COVID, it's a little simpler. He never enters the nucleus because he's a normal virus. He has his vRNA, which enters, gets dissolved via endocytosis, and his viral RNA, which is 5' to 3' positive, can start forming more viral RNA, can form more proteins, And I apologize. Sorry. He doesn't do that immediately. This first forms the antisense that can go through this. So I apologize. This now can form your viral RNA positive again. So this thing again. It's going to form a lot of this. It's also going to form your proteins. And that's like your capsids and your nucleocapsids and all that. It's going to form the glycoproteins that line the cell. It's going to then bind to this. It can leave the cell as COVID. So it doesn't really affect the cell that much, and that's why it's not a particularly deadly disease. But it has a very kind of, sophisticated mechanism. Like it's very simple and effective. So that's the life cycle of SARS-CoV. And that's all the virology you need to know for this exam. Thank you.